When we looked at rate laws, we talked about the exponent in the rate law expression being an order of the reaction. So now we're going to take a look at how do we determine the order of a reaction. First, what we're going to do is we're going to look at a new reaction. We have two dinitrogen pentoxides, and they are reacting to form 4 nitrogen dioxides plus oxygen. What we need to do, first of all, is here is data on the right in the data table where we have concentrations and times recorded. So we're going to take that information and we're going to graph it. And so here we have a graph of concentration versus time. And what we see is we get a curve, which is what we would expect because as time goes on, the concentration of our reactant is going to decrease. What we need to look at now is the rate of the reaction, which is the slope of the line, at 2 different positions. So first we find the rate of the reaction when I have a concentration of 0.9 molar, and I get a rate of 5.4 times 10 to the negative 4 moles per liter seconds, which is the same as 1 over molarity times seconds. I'm going to take a look at the rate of the reaction when I have a concentration down here, and this is 0.45 molar of my initial concentration. I get a rate there of 2.7 times 10 to the negative 4. And when I look at that information, the concentration goes from 0.9 to 0.45. So the concentration is half as big at my second time. If I look at the rates, I'll see that the rate for the second data point is half the rate of the first. And we see that the rate change is directly proportional and equivalent to the concentration change. And what we find is when the rate doubles as the concentration doubles, we have a first order reaction. When we have a first order reaction, our N value equals 1. In this reaction, we only have one reactant, so it was fairly easy to find the order. When we're looking at reactions that have more than one reactant, what we want to do is we want to look at the initial rate. And the initial rate is going to be the very beginning where the slope of the line is fairly straight, where we have very little reactants decomposing, very little of the products forming, and so we're looking primarily at concentration of reactants. What we're going to do is we're going to run several reactions, and we're going to vary the concentration of each reactant one at a time to see how the rate changes with each reactant change. If we look at a new reaction, we're looking at the change in concentration, and we're looking at the initial rates for this reaction of ammonium ions plus nitrite ions, and that gives us nitrogen plus 2 waters. We can write the rate equation, which is the rate equals the change in concentration over the change in time, and that rate equation is equal to the rate law for the reaction. So it's K times the concentration to the N order times the concentration of our second reactant, nitrite, to the M order. And how do we figure out what the value for M and N are? We're going to do a series, in this case, of 3 experiments. In the first 2 experiments, we keep the concentration of ammonium constant, and we vary the concentration of nitrite. The concentration of nitrite is affecting the rate of the reaction. As I go from experiment 1 to experiment 2, I double the concentration. If I look at the rate for reaction 1 compared to reaction 2, what I see is the rate doubles. Since the concentration doubles and the rate doubles, the value for M, which is our order for nitrite, is first order. So M equals 1. Now I'm going to do the same thing and look at, in this case, experiments 2 and 3, because for experiment 2 and experiment 3, the concentration of nitrite is kept constant, and the concentration of ammonium ion doubles as I go from experiment 2 to 3. So now if I take a look at the rate, as I go from 2 to 3, here's my rate for experiment 2, here is my rate for experiment 3. So based on changing the concentration of ammonium ion, doubling it from 2 to 3, the rate doubles from 2 to 3. So what that tells me is the value for my exponent, my order for ammonium ion, is also 1. Now sometimes it's not as neat and as orderly as this is. Sometimes you have data that doesn't have you holding a concentration of one substance constant as you vary the concentration of the other. So in that case, what you have to do is a formula that looks like this. And so we're looking at the rate of 2 experiments. So in this case, we're looking at the rate of experiment 2 divided by the rate of experiment 1, and it's raised to some power x. We compare that to the change in concentration of a particular item in experiment 2 and the same in experiment 1, and we look at that. That should then give us 2 to some power. It could be 2 to the first power, then it's a first order reaction. It could be 2 to the second power, then it's a second order reaction. When we're looking at a reaction like this, where it has 2 reactants and therefore each reactant has its own order, so if we look at up there, when we are looking at the overall reaction order, what we're going to do is sum each of our exponents. So in this case, for the reaction that we're given, the overall order is second order, because that's first order for ammonium ion plus first order for nitrite ion, and that gives us a second order overall for this reaction. Another way to look at reaction rates is to look at something called integrated rate laws, where we looked before at concentration versus rate for rate laws. Now we're going to look at the relationship between concentration and time for integrated rate laws. We're going to stick with our same reaction, the 2-dinitrogen pentoxide going to 4-nitrogen dioxide and oxygen. And again, here's our rate equation, and here is our rate law, and we experimentally determined before that it was a first order reaction. Now, to integrate first order reactions, if you're not involved in calculus, you don't have to worry about, well, how do I integrate something? It's a little bit of memorization. So if you can handle the memorization, you're in great shape. We're going to look at going from the rate equation and rate law to the integrated rate law. We're taking this as a unit and integrating this whole thing. And what that gives us is our integrated rate equation, which looks like this. So it's the natural log of the concentration of N2O5, and that equals the negative K, remember that's the rate constant, times time, plus the natural log of the initial concentration of N2O5. The subscript 0 means initial concentration. Now if we look at this integrated rate law, we'll see that it's a straight line equation. So if we graph it, we have the natural log of the concentration on the vertical axis, we have time on the horizontal axis, we get a straight line, we get a negative slope, and that allows us then, if we look at our straight line equation, the slope term m is negative k. And so we can use this as a quick and easy way to find the rate constant for a first order reaction. Another way to write the integrated rate law is to combine those natural log terms, reshuffle them a little bit so we get rid of the negative sign and we get the natural log of the initial concentration over our concentration at time t equals k, the rate constant, times t. So there are 2 different ways that you can write this equation. Unfortunately, these equations are not on your green sheet, so these are ones you're going to have to memorize. If I want to integrate a second order reaction, I'm again going to start with the rate equation, which is here, and the rate law, which is here, and I'm going to integrate that. So I'm going to take this whole thing now and integrate it, and what I get this time is an integrated rate law that looks like this. So I have 1 over the concentration of my substance equals KT, the rate constant times time, plus 1 over the initial concentration of my substance. So I can try graphing natural log of concentrations. If I do that, I'm going to get a graph that looks like this, that I have a curve. However, if I graph 1 over the concentration versus time, I get a graph that looks like this. So this is linear. Again, since it's linear, since I have a straight line equation, the slope of my line is going to be the constant. So I have an easy way to find the rate constant if I know my reaction is first order or if I know my reaction is second order. Another thing that's nice, especially if you know how to use lists and graphing on your graphing calculator, is you can enter the concentrations, you can enter the times, and you can graph concentration versus time. You can graph natural log of concentration versus time, and you can graph 1 over the concentration versus time. And whichever one gives you a straight line slope, that is the order of your reaction. So if you graph concentration versus time, natural log of the concentration versus time, and 1 over the concentration versus time. Whichever gives you a straight line gives you the order of the reaction.